And I'm going to share my screen. Maybe I really shouldn't have shown Penny the Jurassic Park thing yesterday.
Nah, she's tough. I feel like she's like not the average kid. I feel like she's like super.
I think partially it was because I first saw Jurassic Park when it came out and I was 8. So I'm like, she's 8, I was 8. You know, like
look at the math
I loved
she does
it.
on the board. She's obviously logical. She knows those things can't actually happen.
Yeah, and I think that it really, I mean, it seemed to really make a difference after.
Yes, they can.
I felt really bad because at first when she was like, this is horrible, this is horrible, this is horrible, and she was all nervous about it. It was so sad because she jumped out of her seat when like the T-Rex was attacking them, and she like jumped out and she like looks at me and her eyes are all wild, like we gotta get out of here, like scared, you know. And I was like, oh no, honey. So I've been meaning to do this. So it really, I think it was really helpful for her, for me to be like, let me tell you exactly what happens, you know? All right, so let's start this. I do need a book.
So were you like super good at math when you were in high school?
Yeah, I mean, I was pretty good at school. I was a valedictorian.
So you were first in your grade?
Yeah, and scored really high in the ACT. I got a bunch of scholarships to college, that kind of stuff. So math, I think, actually was my worst subject. As far as like the ACT goes and stuff, I did the worst in math. I got a perfect score in English.
You got a 36?
In English. But pretty good at the other stuff. But the math stuff, I never could get like a super high score in because I couldn't do math that fast.
Mm-hmm.
I'd get like through like there's like 60 problems on the ACT. And at that point in my life, for sure, I was getting through like 50 problems and doing pretty good, but like just guessing on the ones I didn't get to. So that was a big challenge. Yeah. I, you know, just because you're school smart doesn't mean that you're all the way smart all the time, but I was school smart at least. Okay, so if a population is, okay, if a population is not normal, but you take samples where the sample size is greater than or equal to 30, then the sampling distribution of the sample means is approximately a normal distribution. This is a very hard thing to understand. And we're going to go through this in just a second. Not normal and normal. Here's a big important word that you guys need to notice on this. It's all about sample means. I am sharing my screen, right? Everybody can see what I'm doing? Okay. So you know how like that chart that we've been using in the back of the book on A16, it's all based on like a bell curve, right? Mm-hmm. And if data isn't in a bell curve, we can't use that chart because it doesn't make sense to use, you know, that model if the data doesn't look like that. But what the central limit theorem says is essentially, even if a population is not normal, if you look at all the means that you could get, that the means will be normal as long as your sample size is greater than or equal to 30. Okay, now this one doesn't have a sample size greater than or equal to 30, but it does kind of show you what we're looking at. So I want to try this with you. We're going to skip this for right now and go back to it. So we need to write down, let's see, there are the values 1, 3, 5, and 7, and doubles in there. On a slip of paper, you put them in a box, you randomly select 2 slips of paper, okay? So we're assuming that you could possibly get, like there's maybe 2 slips of paper that say 1, there's 2 slips of paper that say 3, so you could get 2 3s, 2 5s, that kind of stuff. All right, now we're gonna do samples of size 2. That means we're picking 2 slips of paper and we're gonna write them down. So I'm gonna really give myself space here. All right, so somebody tell me what's an option? Let's be systematic.
3,
But you're trying to get 2 slips of paper. So tell me 2 slips of paper you could draw.
3 and 7.
A 3 and a 7, that's definitely true. Let's be systematic about it. So let's start at the beginning though. You could get a 1 and a 1, a 1 and a 3, a 1 and a 5, right? It's easier to be systematic because then we know we're not missing anything. Okay, a 1 and a 7. All right. Then we could get a 3 and a 1, a 3 and a 3. And does everybody understand that a 1 and a 3 and a 3 and a 1 are different because of the order in which you pick them in? I know that the results are the same. Okay, so now what we're going to do is we're going to figure out the mean of all of these. And the nice thing is that the mean is very easy to figure this out. What's the mean if our numbers are 1 and 1? What's the average then? Do you guys know what I'm asking?
It's like 1 out of 16.
No, I'm not asking a probability. I'm saying a mean, like an average, right? Let's try this one instead. If I had the number 1 and I had the number 3, what's the average of 1 and 3?
Oh,
2.
Oh.
Okay. What's the average of 1 and 1?
1.5.
Just 1,
Oh, yeah.
right? Because they're both 1, so the average has to be 1.
Mm.
Or if you want to think about it this way, you add them together, you divide by 2. So 1 plus 1 is 2, 2 divided by 2 is 1. It's okay. It's all right. What's the average of 1 and 5?
3.5.
Just 3. Halfway between 1 and 5 is 3. Having a hard day in this classroom. How about 1 and 7, guys?
3.5.
Let's see, what's halfway between 1 and 7?
4.5. 4.
4.
It's not 4.
Yeah, 7 plus 1 is 8 divided by 2 is 4.
Oh.
Okay, we can do this. What's halfway between 3 and 1? 2. It's the average of 3 and 3. Mhm. Average of 3 and 5?
4.
Yes. 3 and 7?
5.
Yes. Okay, 5 and 1.
3.
Mm-hmm.
Oh,
Oh, she's on it now. It took her a little bit. 5 and 3?
4.
4. Nice. 5 and 5.
5. Yeah.
5 and 7?
6.
Yes. It's a race now, guys. 7 and 1?
4.
Yes. 7 and 3?
5.
Yes. 7 and 5?
6.
Yes. 7 and 7?
7.
Ooh, she got all of those, Michaela. You got too giggly. All right. So I'm going to show you 2 things. The first thing I'm going to show you is this. We're going to make a quick graph of the original data set. Okay, so I'm going to call this the OG data set, and this is the X's down here. There's what, 1, 3, 5, and 7. So this is 1, and this is 3, and this is 5, and this is 7. And we're going to talk about right now, like the probability of you getting each one of those is what? If there's only 4 choices in a hat, what are your chances of getting each one?
1 out of 4.
1 out of 4. Okay, so like here's 25%, which is 1 out of 4. And you see how if I graph them right now, they're all the same, right? They're all at 25%. This is called uniform. This is definitely not a bell curve. That's just they're all straight across, right? Okay, so now let's look at the probability of their means. All right, choices we have this time. Looks like we have the numbers for the means. 1, 2, 3, 4, 5, 6, and 7, 1 through 7. Here's number 1, number 2, 3, 4, 5, 6, and 7. Okay, now we know it's out of 16, right? So I'm going to put here 1/16 on the side, 2/16 on the side. I know that's not reduced, but it's just easier. 3/16 and 4/16. Okay, how many ones do you see out of our means? No, I mean like the means. Remember, the means are over here. Here's the means. There's the means.
Oh, 1.
There's a 1, 1. Okay, so I'm going to highlight as we go. So there's 1, 1. So that is 1/16. Yep.
Oh, okay.
How many 2s we got?
2.
2.
Oh, I see that.
Ooh.
3 3s.
Ooh, look at you do have a pattern.
4 4s.
Okay, slow it down, Megan. All right. Look, we don't need a genius here.
I told her the answer. She's using that.
But there's 5. Oh, there's
How many 5s?
4. 3. 3, it's going down now.
What? Just in case you guys aren't excited at home, we're excited in here. But let's be honest, Megan's been excited since I mentioned Pi Day.
Yeah.
He's hyped now.
All right, 6. The hype's matching what I'm feeling. 2 6s, 7,
1 7.
1 7. Okay, so do you guys see how even though the original data set was uniform, that the means are starting to make a bell curve?
Yeah.
Okay, so if I was going to draw it in, I'd be like, okay, so see, we're getting pretty close to a bell curve now. And the more stuff you start pulling, the more samples we have, right? This is just 16 samples. The more samples we have, the more it would look like a bell curve. That's why it is specifically up here that we're talking about the sample means. So even if something's not normal, but if you have n greater or equal to 30, then their means are normal. And if the population was already normal, then their means are normal, no matter what. Okay. And then we have certain formulas for different stuff. Okay, so that the mean, it looks confusing, but here's what I want you to write. So everybody write it down. Okay, so that is, okay, I'm gonna fix that. Hold on, it looks horrible. It's hard to even understand what I'm going for. Okay, so the mu and then sub underneath it is like a little X bar. So it's mu sub X bar equals mu. Just write it down for now. I'll explain it in a moment. And then sigma squared, which is the variance, but you're going to put a little X bar sub beneath it, equals sigma squared divided by n. And sigma with a little X bar beneath it equals sigma divided by the square root of n. So basically what it's saying is that if you look at all the means, the mean of the means is the same as the original mean. And we're going to use this in just a moment. Okay, so if you're like, I don't know how this applies, we'll be doing this lots. So don't worry. The variance of the means is the same thing as the old variance divided by n. And the standard deviation of the means is the same thing as the old standard deviation divided by the square root of n. This is also called the standard error sometimes. All right, let's jump to page 2. Anybody need me to go back at home? Krista, I can't see you. Now I can. Mitchell, you still there? Okay. All right, cell phone bills for residents in a city have a mean of $47 and a standard deviation of $9. I'm going to write down mu is 47 and the standard deviation is 9. Random samples of 100 cell phone bills, so n is 100, are drawn from the population and the mean of each sample is determined. Do you see how it says we're doing samples of the phone bills and then we're looking at the means? So that's how you know this is a central limit theorem question. Find the mean and the standard error of the mean of the sampling distribution. Okay, so the mean of the means is the exact same thing as the original mean, which is still 47. And the standard deviation of the means, if you look back at what we wrote down, it's sigma squared divided by n. So I'm going to take 9 squared and divide by 100, which is 81 out of 100, which is what, 0.81? And then to find the standard error, you could just take the square root of this, or you could say, okay, it's, I believe the formula on the other page was sigma divided by the square root of n, so that'd be 9 divided by the square root of 100, which is what? So 9 divided by 10 is
10, or
point what?
wait, it's not 10.9.
Point what? 0.9.
Oh,
Whoa, guys.
10.
she said that.
9 divided by
I had the
10.
point right. I
Ten.
didn't know what's after that.
This is the hardest section in this chapter for sure, just because it's kind of hard to understand what's going on. Okay, let's try example 3. Assuming that the training heart rates of all 20-year-old athletes are normally distributed. Oh, it says that it's normal. Okay, so it says it's normal here. With a mean of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn, and this size doesn't matter because it said it was normal to begin with. Now see how it says samples are drawn, and now they're talking about the means of all the samples. So this is what tells you it's a central limit kind of problem. Find the mean and the standard error of the mean of the sampling distribution and sketch a graph of the sampling distribution. Okay, so once again, the mean is the exact same thing it was before. You girls tell me how to do the variance?
18 squared divided by 135.
Yep. No, it's 18 squared divided by n, which is 4. So what'd you get for that one?
81.
Now, if you wanted to, you could just do the square root of 81. Sorry, you could just do the square root of 81 to find the standard error. Or you could do the formula. Either way would work. So you could do what? 18 divided by the square root of 4, if you wanted to find the standard deviation, which is 9. And then if you have to sketch a graph, which could happen on an AP test, it would look like this. Because the means would now be looking like a bell curve. So you would say, okay, here's my bell curve. My mean is 135. And then like one standard deviation away, one standard deviation here. Sigma equals 9. What's wrong? Nice. That's no, that's important. Wow, look at that. Anyway, so that's what they mean when they're doing that. So normally a z-score formula is what? X minus mu over sigma. Do you sing it in your head? Okay. X minus mu over sigma. But instead of mu this time, we've got mu sub x bar, which is exactly the same, so I'm not going to change it. And then instead of sigma, we actually have the formula for sigma is the old sigma divided by the square root of n. So the new z-score formula is z equals x minus mu over sigma divided by the square root of n. All right, time for another contest, I feel. Who wants to guess the average amount of time that a 15 to 19-year-old spends driving each day? How many minutes in America? I'll give you a second to think while I write down your names. And of course, go get some prizes. Megan, Michaela, Crystal, Caitlin, and Tanner. And David's not here. I wonder what you would be guessing, David. All right, what is today, Wednesday? Wild Animal Wednesday? Oh, stretches, okay.
I'm so sorry.
I'm a big fan of the wild animal set. I feel like it's not as high quality as some of the other ones. Well, I'll keep searching. All right, so we've got, looks like a giraffe. This giraffe has some stuff on him. It's been like a sticker or something. Weird. This is the best part of the video for David, waiting while I scrape some sticker residue off of an animal. All right, so there's a giraffe, and we got a camel, and we got a tiger, an elephant, and a lion. So those are your choices. I've also got bouncy balls. If you would like to see, I've got 2 bouncy balls, orange swirl, and I think ladybug. Okay, Megan, what do you think? How many minutes do teenagers spend driving? 26 on average per day. Michaela? 25. Krista? Kind of a jerk
40.
test. 40? Mitchell?
43.
Caitlin?
38.
Tanner?
50.
50? Wow, you guys, that's a lot, even for adults. And remember, it's all 15 to 19-year-olds, including the ones that don't drive. So apparently the average is 25 minutes. Exactly. You're the meanest. I mean, congratulations. But I'm pretty sure that you did it just to stop her. All right. So Michaela, now that your friendship is so good right now, and I'm glad there's not any tension in this room whatsoever, would you like an animal, Or would you like a bouncy ball or an I wonder sign? Will you? Okay, which animal?
I'll have tiger.
All right. So what's the probability that the mean time they spend driving every day? Now, do you see this difference here? Everybody look. What is the probability that the mean time? That is what makes this a central limit theorem question. This is the question that everybody keeps asking me. How do you know when it's a central limit theorem question? Before it just said, what is the probability that the amount of time they spend driving? But now it's the mean time, okay? Is between 24 and 27, 27 point, 27 point, oh, okay. 24.7 and 25.5. So I'm drawing a bell curve. And the standard deviation is 1.5 minutes. So let's imagine that right here is, what was this? 25.5. And here is 24.7. We're trying to find the probability between those two. Now, normally we would do x minus mu over sigma, but this time we're going to do this x minus mu over sigma divided by the square root of n, which I don't have a fun song for. I'm so sorry. So you're going to do two problems. The first one, you're going to do 24.7 minus mu, which is 25, divided by 1.5 divided by the square root of 25.
Wait, how'd you get that? Oh,
Yep. So mu was 25 and the standard deviation is 1.5. The other one is 25.5 minus 25 over 1.5 divided by the square root of 25. And these will get you z-scores. So when you put this in your calculator, make sure that there's parentheses around the top and the bottom. And I'll give you a second to do that. Okay, what'd you get as the z-score for the first one?
-1.
-1.41.
No. I just got -1.
I just got 0.1.
Okay, did you guys put parentheses around this? So you did parentheses around the top and parentheses around the bottom, and you typed in exactly what I said to type in? Oh, yeah, you're right. Oh, that's because we put in the wrong number here, guys. My apologies. Because it's the divided by the square root of n, right? And yeah, the square root of the n is 50, right? Because we had 50 drivers. So my apologies. If you want to bring up the exact same thing you just typed in your calculator, hit second enter, and it'll pull up the exact same thing. You can just change it to 50. But you should get, if you do it right, and I'll give you another few seconds to do it, you should get -1.41 and 2.36 for your z-scores. And then you have to find the probability between them. So if the first z-score is 2.36, we're going to have to look that up in our table. So grab your standard deviation table.
You type the whole thing in at the same time?
Yep. You want me to look at what you did?
No.
Okay.
I see that.
Figure out what was wrong.
Yeah.
What were you missing?
I put an extra parenthesis in, I don't know why.
Okay. So get out your standard deviation charts, and that's in bell curve charts, A16, A17, and we're going to look up the probability for 2.36 and negative 1.41. Did you say it doesn't work when you did this?
Yeah.
Okay. So here, you would delete that one. So on the top, it's just 24.7 minus 25, okay? And on the bottom, do you see how we have opening parenthesis, another opening parenthesis, and then just one closing, so it needs to be.
Oh, okay.
Okay. So we're looking up 2.36 and negative 1.41. So 2.36, I got 0.9909. You get the same thing? And for negative 1.41, I got 0.0793. And then how do we find the space between those two probabilities? What do we do? Minus them. So in your calculator, taking 0.9909 minus 0.0793. So I got 0.9116. Anybody have any questions online right now?
Never mind.
Okay. All right, 2 more questions to go and then we're done. We're gonna try one more question for example 5, and I'm gonna give a prize for this one so that you guys can see if you can do it, okay? All right, so we're gonna go back to this, the mean room and board expense for a 4-year college. Now, let me tell you that this data that they're giving me here is not, it's not recent. It is from, I believe this book is pretty recent, not super recent, 2012. Nope, 2015. So this book is 7 years old. Okay, so 7 years ago, what do you think the average room and board, you guys know what the word room and board means?
Like dorm rooms and.
Yeah, it means room and board. So room means how much it costs for you to live there for a year, and board means how much it costs you to eat food. So room and board is usually some sort of like combination of living expenses in the sense that like where you're staying plus how much you're eating. A lot of dorms and stuff will give you, they'll like give you a meal plan.
Yeah,
So that's in the room and board.
that's expensive too.
Everything's expensive. Okay, so room and board, how much do you think it is? Who wants to go first? How about I start on the other end of the list? Tanner.
Like 12,000?
$12,000. Caitlin?
10,000.
10,000. Mitchell?
6,500.
Hey, Krista?
10,600.
10,600. Michaela?
9,909.
Man, you were playing, she's playing rough, guys. Just in case anybody's wondering, Caitlin, you are the one who got screwed this time by Michaela, and Michaela is thrilled about it, just so we all know. Like, I can't see her smiling, but I know she is. Megan?
14,000.
$14,000. Okay, remember this was 8 years ago, and according to them, that the mean is 9,126.
Kidding me.
which puts
Michaela.
Michaela at it again. 9,126. You're a monster, Michaela. Everybody dislikes you today. Would you like a prize? Which one?
I'll take the draft.
Go ahead. All right. So everybody is going to try this problem and we're going to give a prize out for it. And Michaela, I'm just not going to give a prize to you, okay? Because you're driving me crazy. So you randomly select 9 four-year colleges. I'm helping you out right here. Net N is 9. What's the probability that the mean room and board, see how it says the mean, well, I mean, it says he, but the mean room and board is less than 9,400. Okay. And it assumes that the room and board expenses are normally distributed. So remember, it has to be greater than 30 unless it's already normal. So we're good there. Doesn't have to be greater than or equal to 30. It says that the old mean was 9,126 and that the old standard deviation is 1,500. I'm going to help you get started. Let's draw a picture. And we want less than 9,400, right? Okay, guys, so this process is exactly the same as you were doing like yesterday on that quiz. What you need to do now is not just x minus mu over sigma, but x minus mu over sigma divided by the squared event. Okay, which I don't have a song for. So go ahead, go to it. Ready? All right. How are we doing at home? You need some more time? Yep, a little bit more time. I have a picture somewhere and deep in the recesses of an old phone of Reese Riebel, Sam Pitts, and Ozzy Peshin. And they are playing with farm animals together that they had won. And they've got them like all set out on a desk, and then all 3 of them are sitting around the desk as if like they're playing chess, like with their hands on their gun, their faces like, you know, and they're like, okay, and then the horse has to go into the pen. Yeah, that's where this goes. Yeah, you're right. You know, like it's a cute picture of them all. And that was like for like 4 weeks, they had like a club where they would rush to finish their homework. And then for the last like 10 minutes of class, they'd be like, play farm animals, which I'm very sure they were doing like ironically, but you know how like kids are like, this is stupid, so I'm gonna do it because it's stupid. And then they have like a nice time doing it. And you're like, oh, okay, sure. So just not even a little bit of it was like, hey, remember when we were little boys and we used to play with farm animals? This is fun, right? You know, like kind of whatever. All right, hands up if you want to win a prize. 1. 2 for Caitlin. 3 for Mitchell. Krista is 4. Tanner? No? Two. Who's that? Caitlin? All right, Caitlin, tell me.
Okay, so I had it as 9,400 minus 9,126 over 1,500 divided by the square root of 9.
Mhm.
And then when I did that, I got 0.55.
Yep, and that's a z-score.
And the thing for that is 0.7088.
Right, if you look it up in the table. Now, this is always confusing. I mean, guys, isn't it tempting? Look at this graph right here. You know it's more than 50%, but it's often that we draw graphs that are a little incorrect, right? I mean, just look at the last graph we drew. It looked more like 50%, and the answer ended up being like 90%, right? So like the graphs we draw are sometimes off. So it's tempting at this point when you see something like this to be like, oh, 55% is my answer, but like that's a z-score that you just figured out. So you got to look it up. Great job, Caitlin. Caitlin, one of those look nice to you?
I'll have the camel.
Okay. All right. Last one we're doing, and I'm going to give prizes for both of these. But I want to make it really clear when you use this formula, everybody write it down, and when you use this formula, because right now it's pretty easy to understand when you're going to do what, because this section is all about this. They're going to see this over and over again. But like I'm talking about like on the AP test, like how do you know which one's which? So these are the difference between those two. So maybe you want to write difference right here so that you, just in case you ever want to go back to see what the difference is between the two formulas. Okay, this one says that the average credit card debt, I'm going to write it down, mu is normally distributed with a mean of $3,173 and a standard deviation of $1,120. And also, let's just be scared by that for a moment. The average credit card debt of undergraduates in college is about $3,000. Okay. What's the probability that a randomly selected undergraduate, do you see here that it says that we're selecting one person? We're selecting one person who is a credit card holder, has a balance less than 2,700. I draw a picture here. In the middle, we got that 3,173. Over here, we've got 2,700, and we're trying to find less than that, right? This is just like what you did before, where you're going to use that x minus mu over sigma to solve it. Now let's look at B. I know you want to solve this one right now, but hold your horses and wait. You select 25 undergraduates who are credit card holders. What's the probability that their mean credit score, you notice how we're not talking about one person anymore, we're talking about a group of people. So what are the chances that them all together are less than 2,700? And you should know that this one is going to be very different than the first one. And I'll explain why in a moment, but it's the exact same looking problem. So go ahead and figure out both. You're going to get 2 z-scores. Remember, this one has this sigma divided by the square root of n, this one doesn't. And then you're going to look up both of them and get an answer. And I will give 2 prizes out. Go for it. All right, everybody in here is done. What people at home? You need some more time, people at home? Caitlin, you can't win again. What are you doing? Krista's ready. Tanner, Mitchell, do you need some more time? Okay, a little bit more time. Blah. No. So when you use a French press, there's still some sediment that goes into your coffee. It's at the very bottom of my coffee. It's like super.
I hate that
Do you use a French press at home?
sometimes. That's like my thing. I can't use a French press because like sometimes there's grounds and I cannot stand grounds. Like I cannot do it.
I can definitely have no problem with having like, I'm very good at using a French press, so I know how to prevent there from being grounds in there, especially because I grind it pretty coarse.
Yeah.
But there's still like that kind of sediment at the very bottom, which is not really grounds, it's more like a,
Like a paste almost.
yeah, like a
it's
paste.
Like it's like a really thick
Right.
water.
Yep. Kind of like when you mix cornstarch and water and you got that kind of weird stuff. Okay, so we're ready? Mitchell, you want to be in on this contest? Yeah, all right. So Mitchell's number 1 and Chris is number 2 and Megan's number 3. All right. All right, so number 2 and then number 3. So Mitchell, you're first. Do you want to do A or B, Mitchell?
I thought it was 1.
What's Mitchell 1?
You said I was 1 and then you said next person.
Okay, no, I'm not paying attention. Chris, are you 2?
Yeah, I think I might be.
Oh, my bad. Okay, Chris, which one do you want to do?
I'll do the second one.
Okay. So tell me, what did you get as a Z-score?
I got negative 2.11.
That's totally correct. Sorry, my bad. So I've got a Z-score of negative 2.11, and when you look that up, what did you get for probability?
0.0174.
That's exactly right. Nice job, Krista. Animal bouncy ball, I'm a winner.
I'll do an animal.
Elephant or a lion?
Lion, please.
Lion. Do you already have an elephant?
Yeah.
Okay, so we can give you another option if you want. I'm not gonna give you only that option. Okay. And then Megan.
I got negative 0.42 for the
Mm-hmm.
thing and then it's 0.3372.
Okay, now for a big prize today. And I'm sorry, David, that you're not involved in this, but also, David, you have 1,010, so you're okay. Megan, quick, do you want a camel, a lion, a bright yellow moose to replace the one that you gave Clark, a tiger, or a elephant? Or bouncy ball, or an winner side?
I can't remember if I have a lion or a tiger. I think I have a tiger, so I'll take the lion.
All right. Good job grabbing that. What if I had just like snatched it back, like right when you were about to grab it? Good thing that you grabbed it quickly. All right. So here's the big question, and this is worth a fancy pen. So let me get out my fancy pens. This is a hard question to answer.
The lion could take on this.
And everybody's in for this. So even if you already won a prize today, even you, Michaela, who did it
No, not Michaela.
dastardly is what you did.
No.
Okay, so I've got light greens, dark greens, a pink, orange, and a red. Okay, so the question is this. Why does it make sense that an individual person might have a 33% chance of being less than that amount of money, but the mean of 25 people has not a very good chance of being less than 2,700? Why is it much more probable that one person would have credit card debt that's less than 2,700 compared to the average being less than 2,700? Tanner, are you involved in this one? No, not even for a pen. All right, Chris is number 1, Caitlin's number 2, Mitchell's number 2, Megan's number 3. No?
No, wait. Mitchell's number 3, I'm number 4.
You're number 4, thank you. Can't count. kind of important as a teacher. What?
What number am I? Because you said 2 twice.
You're 3.
I'm 3. Okay.
Krista's 1, Caitlin's 2, Mitchell's 3, Megan's 4. My bad. Okay, here we go. And everybody understands the question, right? Question is, why is it a lot less probable that the mean would be less? 4.
Okay, so, like, the one person would be like, oh wait, say the question.
Okay, so the
again.
question is, why, if one person is less than $2,700, their mean is like, their chances is like 33% that they might be under there,
Okay,
right?
So,
But the mean has a lot less of a chance of doing that.
so like the mean is like a lot of different people put together, so like it's a bunch of different scores ranging from like over that to under that, and so like putting that together, whereas like the one person, it could be a lot closer to that because it's not a bunch of different things like put together and made like a big
Right,
little smashed together.
exactly. The chances of you having an outlier is really unlikely if it's a mean, right? If I said, what is the average credit card debt of these 25 people? I doubt we'd have a super high number and I doubt we'd have a super low number because everybody kind of pulls each other together. But if you have one person, they could easily have a high number or a low number by themselves. Okay? All right, so that's it for online today. You guys can sign off when you're ready. Megan. Then you open it and check on it to make sure that it still works.
Yeah,
Awesome. It's 2 pens now.
3 actually.
Oh, dang. All right. Tanner, Krista, Mitchell, don't forget that when you come in that you need to bring in checks for that.
I have a question.
Yeah.
So you said like you circled normally distributed on example 5. I'm just confused. Like, what does that change about how we do things?
Good question. Okay, so at the beginning, it says that if you're talking about the means, if n is greater than or equal to 30, then you can say anything's normal. But if the problem was originally normal, then you don't even have to check that. So Mitchell, in number 5, if it hadn't said normal, then we wouldn't have been able to do that problem because see how the n is only 9?
Yeah.
So it either needs to say normal or it needs to say bigger than 30.
So if it doesn't say normal or bigger than 30 and
you
the
literally
n
can't do
is
that
small, and the n is smaller than 30 before they said any of it,
Right.
you just put can't do on the problem.
Yep. It's impossible to do.
Right, thank you.
You're welcome. Bye.
Yours is fat and lazy. Look at how fat